In the last video, we talked about how there are three different classes of elements. We have the metals, the metalloids, and then the nonmetals. And so with this video, we are going to get a little bit more detailed about each of these three classes. So we're going to start with the metals. Remember, the metals are located on the left-hand side of the periodic table. And this is a class of elements. They're good conductors of electricity and also heat. This is the largest of the three classes of elements. So like I said, they're good conductors of electricity and heat. They have generally high melting points. So we're talking upwards of 1,000 degrees Celsius. And at room temperature, they would be solids. The one exception to this is mercury, Hg, is a liquid at room temperature. Other characteristics of metals is that they are shiny, they're ductile, and malleable. And so ductile means they can be formed into wires. And malleable means that they can be hammered into thin sheets. So think like aluminum foil there. It's very thin. Metals, here's a couple examples. They're shiny because they reflect a lot of light, so this would be a silver tray. They're ductile, so this has a spool of copper wire. And then, like I said, our aluminum foil represents malleability. Nonmetals are a class of elements. They do not conduct electricity or heat. This would be your second largest class of elements, and these includes helium, carbon, and oxygen. Generally, the properties of nonmetals are opposite of those of metals. So where metals had high boiling points, nonmetals will have low boiling points. Metals were solid at room temperature, and nonmetals will actually be gases at room temperature. However, there are several that are solids, such as carbon and phosphorus, but instead of them being shiny, they're dull, they're brittle, and they break. There's no way they could be stretched into wired or hammered into sheets. Bromine is a liquid nonmetal at room temperature. They are poor conductors of heat. Instead, they are used for insulating. They're very good at keeping heat in. So downfilling for a jacket is most likely filled with air, such as nitrogen and oxygen. It's good for keeping you warm. And so here we have some examples. The yellow is sulfur. It's a nonmetal. They've been ground up into a powder, and this has been ready for a shipment. Lead is actually graphite, in pencils anyway, and it's a nonmetal of carbon, or a form of carbon. It's brittle. It breaks easily if you put too much pressure on this. I think we've all probably experienced that. And then the heads of matches are coated with the nonmetal phosphorus. It's not malleable, and if you tried to pound it flat, it would crumble into a powder, much like the graphite did in the pencil. The last class is metalloids. This is a class of elements. They have some properties of metals and some properties of nonmetals. So they're located in between the metals and nonmetals on the periodic table. And this is the smallest class of elements, and there's only 7 of them. Many of them can conduct electricity, but only at certain temperatures. So we call them semiconductors. So for example, silicon is used in computer chips. It's the most common metalloid on Earth. It's shiny like a metal. However, it's brittle like a nonmetal. So this is just showing you how metalloids have both metal and non-metal characteristics. So there's your examples. There's silicone. It can conduct electricity, but not as well as the metal. It's shiny, but brittle. It chips easily, kind of like glass. Antimony is another metalloid, shiny like a metal, but it's brittle. And then boron is a metalloid, somewhat shiny. It also conducts electricity like a metal. However, it is also brittle. And so there's your examples of metalloids. So when we look at an element, chemists really like to investigate electrons because electrons are involved with chemical bonds. So when we look at each class of elements, we notice that each element from left to right has one more electron than the element before it. So electrons are added to the lowest possible energy level until that energy level is filled. So increasing the number of electrons explain why elements go from metals to metalloids and then nonmetals. So it's really these electrons that are the deciding factor if an element is a metal, metalloid, or nonmetal. And so here kind of shows you this electron filling. So lithium has 3 electrons, valence electrons, just total electrons. And so this pink ring is indicating the first energy level. This purple ring is indicating the second energy level. And then the green ring here indicates the third energy level. And so lithium has 3 electrons, so we have to fill this first energy level first before we can place this final third electron. Again, looking at boron, boron fills the first energy level right away with 2 electrons, and it still needs to place 3 more so they can be put in the second energy level. They cannot go into the third energy level because the second energy level isn't full yet. Fluorine, same experience, fills that first energy level very quickly with 2 electrons, but it still needs to place 7. 9 minus 2 is 7. And so those 7 go into that purple second energy level. And we can't place any of those in the third energy level because that second energy level isn't full yet. Remember, that second energy level can take 8 electrons. So finally, as we work our way to the very end of that period, we get to neon, which has 10 electrons. As you can see, that first energy level fills up with 2, and then we can place the remaining 8 in the second energy level. So that fills the second energy level. So when we get to the element which is next in line, which is sodium, we'll have 11 electrons. That 11th electron will go in the third energy level. So valence electrons are actually the most important electrons, and these are the electrons in the outermost energy level, and these are the ones that are involved with any type of bonding that element might do. So if we go back here and look, the elements in the outermost, so for lithium, this 1 electron right here is in the outermost energy level for lithium, and so therefore lithium has 1 valence electron. If you look at boron, its outermost energy level that has electrons is again that second one. And so to figure out the number of valence electrons, you just count how many electrons are in that outermost energy level. And here we have 3 valence electrons. Same thing with fluorine. To figure out its valence electrons, look at the energy level that has or is the furthest away from the nucleus and count how many valence electrons are located within that energy level. And for fluorine, it would be 7 valence electrons. Lastly, looking at neon for valence electrons, look at the outermost energy level. Again, in this case, it's only the second one. And you'll see that there are 8 valence electrons in that energy level. And so neon has 8 valence electrons. So the number of valence electrons determines how likely an element is to react with other elements. And so it also indicates the ability to conduct electricity because the electric current is the flow of electrons. So, looking at their valence electrons and reactivity by classes, metals, their outermost energy level is almost empty, meaning they probably only have 1 or 2 valence electrons, and they want to get rid of them. This would then allow them to have a full outer energy level. So let's go back here again. If lithium, which is a metal, were to give up this 1 valence electron and it were to go away, then its outermost energy level now is energy level 1, and it is full. This is what elements strive for, is to have a full energy level. So this makes metals very reactive, and they're good conductors of electricity because those valence electrons have a very easy time or easy ability to flow. Metalloids, their outer energy level is about half full. So they can either gain or lose electrons in order to achieve a full energy level. And they might be able to conduct electricity, but usually not very well. And like I said earlier, it's usually very temperature dependent. Nonmetals, their outer energy level is almost full. So they're probably looking at 6 or 7 valence electrons. And they want to gain 1 or 2 electrons in order to get that full outer energy level. That makes them very reactive, like the metals, but they only accept electrons. They do not give them up. And this makes them not conduct electricity because they do not want to give up those electrons, so those electrons cannot flow. And there's other nonmetals that have a completely full outer energy level. This is usually your group 18. The electrons are already in their stable arrangement. That outer level is full, so that makes them unreactive. Oops, sorry. And they cannot conduct electricity because those electrons will not flow. So here's our examples. Lithium is a highly reactive metal. It has that 1 valence electron, and it's explosive with water. Boron is a metalloid, 3 valence electrons, and it's less reactive than lithium. Bromine is an extremely reactive nonmetal. It has 7 valence electrons. And then neon is a nonmetal. It's a gas, and it has that 8 valence electrons. So it's got a completely full outer energy level, so it's not reactive.